This lesson is about relativity, and it's going to only be about Galilean relativity. This is the old regime, so to speak. It's making way, or making ready, our approach to special relativity, which will be quite a bit different, but the general ideas and the way we think about things will be similar. So, to start with, I should point out that the kind of reference frames that are valid, where Newton's laws are valid, are called inertial reference frames. Okay, so what is an inertial reference frame? So an inertial reference frame is a frame where the sum of the forces is equal to 0. Okay? So that means there are no accelerations in the reference frame, right? That is, the reference frame itself is not accelerating. Okay?
Okay.
So how would we know if it is? Well, we'll construct an accelerometer. Okay, and how will that work? Well, you might recall that we talked about springs and the force that springs provide. Right? You remember that the force of a spring is equal to some spring constant, which describes how stiff the spring is, times the displacement from its equilibrium point.
Right.
So if at rest the spring is naturally like this and you try to squish it in or stretch it out, it will pull back with a force that is linearly proportional to the displacement in the spring equilibrium that you make. Okay? And so we can construct an accelerometer. And it'll basically be a cube with 6 springs in it, but I'm going to show you one axis at a time. So we'll have a wall of our little box. Here's the spring. I'm going to put a ball in the center of it. And then we'll have another spring. I guess we'll go like this. Now the springs themselves we'll assume are identical in every possible way. The ball, right, if you try to move the ball, there will always be a force, right, opposing its motion, right? So if I try to move it this way, right, there'll be the force of the spring making a kx in this direction, right? And there'll be the force from this spring in this direction trying to restore it back to its equilibrium position, okay? And so if there's no acceleration, right, so if the acceleration, we'll call this the x direction. If there's no acceleration, then we would expect that this ball would be lined up in the center, okay? Now we're going to imagine that we've got another one for the y direction and another set of springs for the z direction, all attaching to this ball. So this ball will move either left and right, up and down, or forward and backwards, depending on whether or not it's going to sense an acceleration in one of these directions. Okay? And of course, it could be on a diagonal direction too, but that's beside the point. So we expect it to sit stationary in the center if we're not feeling an acceleration. But what happens if we do feel an acceleration? What would that look like? Let's say there's an acceleration in the x direction. So that's this direction. We're accelerating in that direction. The acceleration in the x direction is equal to some a, right? And it's in this direction. Well, that's going to cause the spring to, because remember, the motion of the ball is simply because it's resistance to change its state of motion. Okay?
All right.
So it's like when you're in a car and you hit the accelerator, you feel like you're being pushed back in your seat. The ball will push back in its seat, so to speak, right? And this will result in this stretch state of the spring. So we see that it's now displaced from its equilibrium, right? We have the spring constant kx plus this acceleration a in this direction minus the spring in the other direction, right? Will just leave us with a. And so our acceleration in the x direction will be this a acceleration here, right? And so using this little box, we can tell whether or not we're in an accelerated reference frame, okay?
Okay.
We will see the ball moving, okay?
All right.
So another way to say that is that acceleration is an absolute quantity, okay?
Okay.
If you have one of these accelerometers, then you can determine whether or not acceleration is taking place if your reference frame is accelerating. All right? Now, physically, it's easy for you to understand that because you can imagine being on a skateboard. If the skateboard is accelerating, you're going to feel it because you're going to feel like you're being thrown off balance, right?
All right.
Because your body wants to stay in its same state of motion. The skateboard is changing its state of motion, right? And so you're going to have to compensate for that somehow. Make sense? So that's the effect of being pushed back in your seat or whatever. Or if you're on a merry-go-round, you feel like you're being thrown outward right from the center as you spin around. These, by the way, are called pseudo-forces. They're not real forces. It's not a force because of, say, gravity or, it's not a magnetic force or anything like that.
Yeah.
Right? It's a pseudo-force because of the coordinate system that you're employing, basically. Okay?
All right.
And we'll talk much more about that when we talk about the basics. When I say basics, I mean the basics of general relativity. Okay? So we'll discuss pseudo-forces versus real forces. But anyway, so this is an accelerometer. The notion here is that acceleration is absolute. we do not need to refer to another frame of reference in order to make statements about the acceleration. We can know just simply by having an accelerometer in our presence whether or not we are accelerating. Okay?
Okay.
What about velocity? Is velocity absolute? Well, what do I mean by velocity? Let's imagine a little vehicle with some wheels on it, traveling with some velocity in that direction. Yes?
Yeah.
On some, driving surface, right? So that's what I mean by velocity, is that it's traveling, it's traveling some distance in some interval of time.
Yeah.
We'll assume that it's constant velocity, so it's not accelerating, it's just traveling at some constant velocity, right? But now let's imagine that this driving surface that we're on is actually a ship. And this ship is traveling in this direction with some velocity v. I'm going to denote this minus v, okay? But what do I mean by that? I'm not saying that it's going at a velocity v with respect to this little car on top of it. What I mean when I wrote that is that there's a shore, right? And there's a guy standing there on the shore watching the ship pass by. And with respect to his reference frame, this is the relative velocity that we see.
Yeah.
So when you're in your own reference frame, you always think you're stationary. Okay? I know that's a little counterintuitive because we think when we're riding in cars, we know we're moving because we feel the vibrations of the road and stuff like that.
Yeah.
Okay, but you're feeling accelerations. Okay? If you were driving on a completely smooth surface, or if you were maybe in a spacecraft that was traveling at a constant velocity,
Yeah.
you would not be able to tell. Okay?
All
There'd
right.
be nothing you can do. Galileo, when he wrote about this, he talked about all these different things that happen inside this moving room. It was on board a ship, of course,
Yeah.
right? Talked about, I don't remember all what they were, but bug flies flying around the room and stuff. Everything looks normal, just like it does when you're at rest on the surface of the Earth, right?
Yeah.
So you cannot discern that you're undergoing, that you have some constant velocity, okay?
All right.
So this velocity of the ship, right, from the ship's perspective, it's not moving. It's stationary and everything around it is moving. The guy on the shore is going by in the opposite direction, right?
Yeah.
The car, of course, is moving relative to the ship, right?
Yeah.
This velocity, by the way, minus v, is relative to the ship, right?
Yeah.
So, and if we think about what does this guy see, I'm going to move the guy so that he is directly lined up with the little car on the ship, right?
Yeah.
If this is going v in that direction relative to the shore, and the car is going with minus v in this direction relative to the ship, right? From the perspective of the guy on the shore, right? The car is not moving, right? So we'll call this double prime, we'll call this prime, and we'll call this v, the velocity of the little car in the unprimed frame, or this stationary frame here, is going to be equal to the v prime minus v double prime, but the magnitude of these things are the same, right? So if I write that v double prime is the magnitude is equal to the magnitude of v prime, and that's equal to just some number v, right? Then we can write this as v minus v equals 0. So the relative velocity of a little car on the ship is 0 with respect to this guy on the shore.
All right.
Right? So you've got the ship going this way, the car going the same speed in the opposite direction, and so from the perspective of the shore, they're just not moving. The car is not moving, you see?
Yeah.
I think I did that right. Sometimes you have to think about these to make sure the numbers work out. You have a question?
Is the ship infinitely long?
In this case, yes. I didn't draw the end of it, so I just assume it goes on forever. But in principle, ships are not. Okay, so that's that. Now, when we talk in relativity, right, so as you can see, velocity is relative, okay? And that's what we mean by it. It's not something you can discern about your own reference frame. You can only specify a velocity in reference to another reference frame, okay?
Okay.
There is no absolute motion. There's no, ether from which we can track an absolute velocity, okay? Now, why acceleration is absolute, that's a little weird, and people debate this all the time, even today. But for our purposes, we'll think of it as an absolute quantity. It's kind of the basis of Newton's first law, right? That things they stay in their state of motion, right? That means that they resist any changes or accelerations. So physical laws are not things you can derive or prove. They are just observations that you make. So we'll think of it as that. So when we talk about special relativity, we're going to use the same two reference frames over and over again. And it's the ones that Einstein used. We're going to use a train and a platform. Right? The platform is on the side of the train. It's on the ground, right?
Yeah.
So we'll have a train, and we're going to make our train basically the cars themselves are big rulers.
All right.
I'll make it the same width here. And we'll kind of make each of the rulers kind of adjacent to each other so there's no like gap in between them. So there's the car, and then we'll have another ruler. And this can be our little engine, and we can have, you know, an infinite number of cars. And next to the train, we're going to have the platform, which is basically a giant ruler, right? Or a set of rulers, usually referred to as measuring rods. When I say measuring rod, I mean one of these things here, between here and here. It's a bar of the same length. And so all of these little tick marks I put are these measuring rods laid out end to end. Okay? And we're going to specify on these measuring rods some origin, right? Some point that we're going to call 0, right?
Yeah.
And no, it can be anywhere, but we're just going to make it here, for example. We'll call this the origin, O. Okay? And on the train, we'll make this guy the origin, O. Just the point from which that, so if the train were making a measurement, measured here, we say that's -1. If we measured this point here, we say this is at the point +1. Okay?
Yeah.
So it's just something to make your references with respect to. Okay? Additionally, on each of these little, where each of these little measuring rods are located, right, at the ends of each of the measuring rods, we're going to put clocks. Okay? I'm not going to draw all the clocks, right? But here's a clock. Here's a clock. Okay? Clocks everywhere in both frames, right? We'll have clocks here and clocks here. Clocks everywhere. At the end of every measuring rod, there will be a clock. Okay? And you can imagine also, if you wanted to, that at the end of every measuring rod, there's going to be a person. Well, you know, if you want to, we can make the person like a clock person. So there's a head. The head is a clock, right? Maybe we call them graduate students. I don't know. But we have observers. We'll call them observers. Okay? At every point, we have observers. And the only thing they're there for is to say what they see directly across from them, and note at what time it took place. They'll say, the time is this. I see this event. Okay?
All right.
I see Robert pass. I just passed Robert. Okay? Or I just passed Fred. Okay?
Okay.
And they'll record the time at which they observed that. Okay?
All right.
So that's what they're doing if we imagine this in our minds. All right. So I know it seems weird, right? I mean, we're doing all this talking around stuff, but it's going to turn out to be important because when we talk about special relativity, we're going to see some rather funny things happen with the lengths of these measuring rods and with the times on these clocks. Okay?
All right.
And so that's why I'm being a little careful with it. Now, visually, how do we graph this, right? So let's start by, let me see what I do in my notes. I started with the O prime frame, the O frame. So I'm going to call the platform frame, and that's a script O. It's kind of like a cursive O, okay? And then we'll have, of course, the reference frame of the train. If we were on the train, I'm going to call that the O prime frame, okay?
All right.
Or this little tick mark at the end there is a prime. Okay?
Okay.
So if I say I'm in the O frame or from the O prime frame, that's what I mean. I'll usually say I'm in the platform frame or I'm in the train frame. Okay? Yeah?
Yeah.
So let's draw a graph. What do we see if I can, of course, make a Cartesian set of coordinates. We'll call this x, and that's the distance from here. The origin, O, is right here. I could draw negative x's if I wanted to. And then we, of course, have t for time. Okay? Now, why it is that in relativity we always use the y-axis for time, I don't know, but everybody does it, so you just have to get used to it.
All right.
Intuitively, we'd usually put it here, right?
Yes.
But it is what it is. Now, the interesting thing is if I plot the origin of the train, this point right here, right? I want to say that I'm going to synchronize our clocks, right? We agree that when our origins pass each other, that we're going to synchronize our clocks. So we're like, hey, get ready for the big experiment. As soon as we see each other pass each other, we're going to start our clocks ticking. And we'll say they start at 12 o'clock, whatever, right? Or 0, okay?
Okay.
Most watches don't have 0 o'clock, but it's easier, working with equations to think of time as just, some number from 0 on instead of hours and minutes. So, but that's the idea. We're agreeing to synchronize our clocks at our origins, right? So when this little observer standing at this origin sees the other observer at the platform origin pass each other, they're going to hit the button to start their clocks, okay? Now they're going to keep time. And so that's what this point here. So at this point here, x equals 0, right? X prime will also equal 0, right? And so the train is here at t equals 0 and t prime equals 0. So this guy's clock says 0, this guy's clock says 0, and these two are lined up. They're occupying the same space, okay?
All right.
But at a later time, of course, we'll see that the train has moved in the positive x direction, right? So it's over here somewhere. This origin, as the train is going by with some velocity v, right, relative to the platform, this origin will move down here in the positive x direction. So it might be, you know, here at some time here, right? So we put that point right there, right?
Yeah.
And in between, there were times in which it was, you know, closer to this x equals 0 point. So as it turns out, this is just, you know, going to be a line. If there's no acceleration, if the train is traveling at a constant velocity, this will be a line, right?
Yeah.
And you could figure out what this line is basically given by t equals v times x. Or actually, really what we want is the other way. I'm going to write it like this. The x value is equal to the velocity times the time, right? So this line has a particular, it's important, and we call it the world line of the train,
All right.
okay? Now each of the other observers on the train will have their own world lines, right? The guy at x prime equals 1, his world line, right, will be located over here a bit, and he will be traveling basically parallel to this guy, right? If I wanted to draw what it looks like from the train's point of view, right? Let's just think about that for a second. I'm not going to go into any great detail on it. Let's say this is my x prime axis, and this is my t prime axis. Remember, I'm using the primes to refer to coordinates in the reference frame of the train. Okay?
Okay.
So when I say prime, t prime, or x prime, that is a ruler or a time in the train's reference frame. Okay?
All right.
So that's either the clock or the measuring rod that's on the train. Okay?
Okay.
So that's what this is referring to, right? Now, of course, to him, his origin is not moving. It's just staying in the same place it's always been, right?
Yeah.
But the origin on the platform is moving in the opposite direction, right? If you were standing here, as it looks to you like the platform is moving by in this direction, minus v. So the world line of this point on the platform in the train's reference frame would look like this, right?
All right.
It's going in the opposite direction. It's becoming, you know, minus x as time goes on. Yes?
Yes.
Okay. So we won't use this reference frame very much. I find it easier to always stick with this reference frame with everything in the first quadrant here, right?
Yeah.
And for the most part, we can do that and get what we need. But let's just look at a few notes here. Another way to think about this line, right, is that this line, this is what I call the world line, this is also x prime equals 0. At every point on that line, x prime is equal to 0. You see?
Yeah.
Now what about this line here, which I kind of drew as a dashed line? That's this point here, right? That's x prime equals 1. X prime equals 1. So if this is x prime equals 1, what is x equal to? Well, that's, to write it in terms of just x, I write it as x equals 1 plus vt. Yeah?
Yeah.
That's not tricky, right? Okay. Additionally, right, there's a time that these 2 points occur, right? And we'll call these a points. If we want to label them, we can say it's an event. Okay? It means we've observed something at that position at a certain time. And so I put a point on it, we call it an event. Okay?
Okay.
But these occur, right, along the time is along here, yes?
Yeah.
So that's going to occur at some time value, t equals 5 or 6 or 7, whatever it is. This would, of course, be where things are at t equals 0, right?
Yes.
And we're going to assume, because there's no reason not to, right, that everything is going to kind of stay the same and fixed. And I'll just show you what I mean by that. So let's see, what are the equations of Galilean relativity? Let's write down what we have. So if we assume that x naught prime equals x naught, which equals, we'll just call it 0, right? And this happens at t prime equals t equals 0. I guess I could have called that naught. What can we write? Well, we can write this equation that we had here, that x is equal to x naught plus vt, right? That's saying that your x position is whatever it was initially, right, which is 0 for us. Add to that the distance that it's traveled in time t, right? The bigger t is, the longer the distance it's traveled, right? So this, we can write this down. We can also write down that x prime is equal to, well, x naught prime. So this would be, for example, at the origin, right? Write those 2 equations down. Let's put a bar under it. Let's subtract them, right? What do we get? We get x minus x prime equals x naught minus x naught prime minus vt. Be plus. So just subtract these two, right?
Yeah.
And what do we get? Well, the x naught minus x naught prime, since we set both of those equal to 0, right, both of these just go to 0 here. And what I'm left with is that x minus x prime equals vt. Okay? Another way to say that is that x prime is equal to x minus vt. Okay, I just solve for x prime. Okay?
Okay.
All right, so we can do the same thing with time. We can solve, get some relationship there. It's kind of trivial, but we can say that t equals t naught, and that t prime is equal to t naught prime. We can subtract those. That'll give us t minus t prime equals t naught minus t naught prime is just 0 because we agreed to synchronize our clocks and set both of them equal to 0. And that just says that t is equal to t prime, or t prime is equal to t. And so in the end, right, what we're going to get are our Galilean transformation equations. We'll have x prime is equal to x minus vt. Okay? That tells me if I have coordinates in the unprimed frame, I can get the coordinates in the prime frame by using this transformation, you see?
Yeah.
It also says that t prime is equal to t. Okay? And then we have what we call the inverse transform equations. Okay? So we'll call this transform, and then we'll have inverse transform. And that will say that x, and you can get these by basically flipping where the primes are,
Yeah.
right? And changing the sign of v to be negative, right? And so what does that give us? Or you can just solve for x, either way. That gives me that x equals x prime plus vt, and that t equals t prime. Okay, so now, oh, this should be t prime, sorry. So that says if I've got a coordinate in the train frame, I can figure out what the corresponding coordinate is in the platform frame using this substitution here. This is called Galilean relativity, okay?
Okay.
And it's not very deep or profound. It's kind of common sense, and I'll show you an example, okay? Why is it kind of common sense? Well, let us consider a problem similar to what we had at the beginning with the boat, with the car driving on the boat, observed by the guy on the platform. We're just going to have a boy running at some speed. We'll call it u prime. He's on the train. We'll put a guy on the train who's running, right? So we'll let a guy be running on the train. He's going in the direction of the speed of the train. So we'll call that u prime. This is velocity, okay? And so the question is, what is his velocity relative to the platform? So if the guy is running at u prime on the train, right, and I'm on the platform, how fast is he going by me? We know the answer. Right? We know it's going to be the speed of the train plus the speed of the boy, right?
Yes.
So they'll add. But let's see how we get that formula using the transform equations, okay? So we first write down u prime, which we're given, right? We know that u prime is equal to his x prime position, right? Divided by, whoops, I'll call it delta x prime, how far he travels on the train, divided by how long it takes him to get there, right? So delta x prime divided by delta t prime, right? That's equal to his velocity. So all I have to do is just substitute in for this, right? And so I'll get, substitute in for delta x prime, I'll substitute in delta x minus v delta t. And we'll divide that by, and I'll also substitute in delta t prime is equal to delta t. So delta t prime becomes delta t. You see that?
Yeah.
I'm going to divide the delta t into both of these terms. When I take it into delta x, we'll get delta x over delta t. And then minus v delta t divided by delta t, right? Delta x over delta t minus v delta t over delta t. Well, look at it. These just cancel, right? Because they're the same.
Yeah.
Delta t over delta t is just 1. And so this gives us delta x over delta t. Well, what do we call delta x over delta t? Well, we call delta x prime over delta t prime u prime because it's in the train frame. So we'll call delta x over delta t u. So this gives me u minus v, right? And so what do I end up with? I get u prime equals u minus v, which means that in the platform frame, u is equal to u prime plus v. So I take the speed of the boy on the train and add the speed of the train to that. And so this is what we have with our common sense notion, right? That the boy will be traveling relative to the platform at the speed of the train plus whatever speed he's running, right?
Yeah.
And we got it kind of formally using these transform equations, okay?
All right.
Now you will not be able to use your intuition with special relativity, okay? Because there's nothing that's intuitive about it, pretty much, okay? So we'll have to rely on transform equations. They're just not these transform equations. They're close, but they're not the same exactly, okay?
All
And so that's what we'll be exploring when we learn special relativity, is how these transformation equations change and some of the weird and wacky effects that they predict, I guess you'd say. And these were predicted effects. Nobody could have ever expected these things to happen. And so it's going to be fun to look at them. We'll have to be very careful about the way we think about it because it can get confusing very quickly. Okay?
Okay.
Galilean relativity, not so confusing. I took a really slow and careful approach to it, but I mean, we could have said it in 5 minutes and you would have gotten it. But I just want to point out the key things, the clocks and the rulers, right? And this is going to be important for the way we think about problems in special relativity, okay?
Okay.
All right, that'll be the next lectures on special relativity.